Now let's take up the next question, dear students. Let's now solve some of the questions which are asked in few previous JEE question papers. The maximum number of possible interference maxima for slit separation equal to twice the wavelength in YDS experiment is options A infinity, B 5, C 3 and D 2. So the condition given here is the slit separation, that is small d, is equal to twice the wavelength 2 lambda. And now we are supposed to find out the maximum number of the possible maxima. Maxima means the bright fringes. So how many such bright fringes are possible when the slit separation is equal to 2 lambda? That's the question asked. So in order to solve this, we need to consider the condition for a bright fringe or condition for maxima is, you know that the path difference delta can also be written in terms of slit separation, that is delta is equal to d sine theta. For maxima, this d sine theta or delta should be equal to n times lambda, that is the integral multiples of lambda. But here d is given to be 2 lambda. So let me substitute for the value of d here. 2 lambda into sine theta is equal to n lambda. Can directly cancel lambda here. But one more important thing here is, in order to get the maximum number of bright fringes, here actually n indicates the order of the fringe or the number of the fringe. In order to get maximum value for n, your sine theta should take maximum value. So for maximum n, sine theta should be maximum. The maximum value of sine theta is 1. Therefore, substituting these in the above expression, I get 2 into 1 is equal to n, or n is equal to 2. So what does this mean? The maximum order of the fringe pattern should be equal to 2, but don't be confused and mark option D as the correct answer, because option D is not the correct answer. N is equal to 2 doesn't mean that the maximum number of bright fringes is 2, because when you have a look at the screen of YDS experiment, you'll come to know this. If you consider this as the center of the screen, you have n is equal to 1 here and n is equal to 2 here. So this doesn't mean that there are only 2 bright fringes. Look at 0. Look at the center of the screen, where also a bright fringe should be formed. So again, don't be confused that there are 3. Again, don't come to a conclusion that there are 3 bright fringes, because on the other side of the central fringe pattern, you have again n is equal to -1 and -2 as well. So that also means that there are 2 bright fringes above the center and 2 bright fringes below the center, and along with a central bright fringe. So totally 5 bright fringes are possible for the given condition. So which means that when n can take a maximum value of 2, the possible or the maximum possible fringes is 5 bright fringes, or 5 maxima are possible. Therefore, option B is the correct answer, that is 5 bright fringes. Now take a look at the next question. In Young's double slit experiment, the intensity at a point is 1/4 the maximum intensity. Angular position of this point is options A sine inverse of lambda by d, B sine inverse of lambda by 2d, C sine inverse of lambda by 3d, and D sine inverse of lambda by 4d. This problem is based on the expression for the intensity or the resultant intensity at any point on the screen. So you should be aware of this formula for resultant intensity at any point on the screen. It is given by IR is equal to I1 plus I2 plus 2 root I1 I2 into cos phi. But when the two intensities are equal. Usually that is the ideal case. That is, when the two individual intensities are equal. This is possible when the two individual amplitudes are equal, and that is possible when the two slits are of equal widths. So, or I'll write this as the individual amplitudes A1 is equal to A2, or you can also call it as W1 being equal to W2, where W indicates the slit separation or the slit width. Right. In such a case, you can rewrite this expression as IR is equal to, you can call this I1 and I2 as equal to I naught. Let me say here I naught. Then you get I naught plus I naught plus 2 root I naught square into cos phi. That gets you an expression for IR, which is equal to 4 I naught cos square phi by 2 as the expression for the resultant intensity at any point on the screen when the two individual intensities are equal. Now, since it is not mentioned in the problem that the two individual intensities are unequal, you can take them as equal. So, when it is not mentioned that the slit widths are different or the amplitudes are different or the individual intensities are different, you can always take the help of this expression for resultant intensity at any point on the screen. That is, IR is equal to 4 I naught into cos square phi by 2, which is to be treated as the most important expression in interference and in Young's double slit experiment. Okay, here you have to consider a particular point on the screen where the resultant intensity IR is 1/4 the maximum intensity, and you should be aware of the fact that at any point on the screen the maximum intensity should be 4 I naught. This particular term 4 I naught refers to the maximum intensity. That should be the intensity at the bright fringe, whereas the intensity at the dark fringe should be 0. So I can write this I max as 4 I naught. In that case, IR gets reduced to 4 I naught by 4, or IR is equal to I naught. Or you can simply call this as I max by 4. Now, let me rewrite the expression for resultant intensity IR is equal to, in place of 4 I naught, you can write I max. 4 I naught is also the maximum intensity, so I'll replace it by I max into cos square phi by 2 as it is, but resultant intensity is given to be 1/4 the maximum intensity, so that is I max by 4 should be equal to I max cos square phi by 2. You can cancel I max here, so you're left with cos square phi by 2. That is equal to 1 by 4. So cos phi by 2 is half, or phi by 2 is cos inverse of half is pi by 3, or phi is equal to 2 pi by 3. So when phi is equal to 2 pi by 3, you can find path difference is given by delta is equal to lambda by 2 pi into phase difference, that is 2 pi by 3. So path difference is equal to lambda by 3. Now you have an expression for path difference, that is delta is equal to d sine theta. So d sine theta is equal to lambda by 3. Therefore, sine theta is lambda by 3d, or theta is equal to sine inverse of lambda by 3d. So this is nothing but the angular position of the point where intensity is I max by 4. Therefore, angular position is equal to sine inverse of lambda by 3d, which is correctly written in option C. Therefore, option C is the correct answer. Now let's take up the next question. The intensity at a point where the path difference is lambda by 6, where lambda is the wavelength of the light used, is I. If I naught denotes the maximum intensity, then I by I naught is equal to options A root 3 by 2, B 1 by 2, C 3 by 4 and D 1 by root 2. Again, this problem is also based on the expression for maximum intensity at any point on the screen, where you can treat that the individual intensities are equal. So the resultant intensity at any point is given by IR is equal to I max cos square phi by 2, where phi is the phase difference between the two individual waves at that point, and I max is the maximum intensity, which can be written as 4 I naught if I naught is the individual intensity. Now, here the resultant intensity at a point is given to be I, and maximum intensity is given to be I naught. So you should be very careful while using these symbols. So I is equal to I naught into cos square phi by 2 is the reduced expression. Now we are supposed to find out the ratio of I to I naught, that is I by I naught is equal to cos square phi by 2, where phi is the phase difference. Now how do you extract the value of phi? But here the given data says that the path difference between the two individual waves or interfering waves is lambda by 6. Let me make use of that. The path difference delta is equal to lambda by 6. When path difference is known, you can always find out phase difference using the formula phi is equal to 2 pi by lambda into path difference delta, that is 2 pi by lambda into lambda by 6. So that gets reduced to pi by 3. So the value of phase difference is pi by 3. Let me substitute this phase difference in the expression for I by I naught. I by I naught is equal to cos square phi by 2 is pi by 3 by 2, which is pi by 6. So pi by 6 is 30 degree and cos 30 is root 3 by 2. The square of this, that is root 3 by 2 whole square, that is equal to I by I naught. Therefore, I by I naught should be equal to 3 by 4. So 3 by 4 is the correct answer given in option C. Therefore, option C is the correct answer. Now let's take one more question on resultant intensity, dear students. At 2 points P and Q on a screen in YDS experiment, waves from slits S1 and S2 have a path difference of 0 and lambda by 4 respectively. The ratio of intensities at P and Q will be options A 2:1, B root 2:1, C 4:1 and D 3:2. Now here let's consider two different points on the screen. Let's write the screen first. Now, if this is the center of the screen O, let's consider two different points P and Q on the screen. Now, just don't worry about the positions of these P and Q. This is just for representation on the screen. Now, at P, it is mentioned that the path difference between the two interfering waves is 0, and we know that when path difference is 0, phase difference should also be 0. And you can find out the intensity at P. Next, similarly, at Q, the path difference is given to be delta is lambda by 4, using which you can find out phase difference as well. But what are we supposed to find out is the ratio of intensities at P and Q. Now, what is IP, which is intensity at P? Whenever the path difference is 0, phase difference is also 0, then it means that the two individual waves interfere constructively, giving you maximum intensity, which is denoted as I max. So the intensity at P should be I max. Now coming to Q. At Q, the path difference is lambda by 4. Therefore, let me calculate the phase difference using the formula 2 pi by lambda into path difference, using the formula 2 pi by lambda into the path difference, which is equal to lambda by 4. So, your phase difference is just pi by 2. When you know the phase difference at any point, you can find out the resultant intensity at that point, which I'll indicate as IQ, is equal to I max cos square phi by 2 as explained earlier. Let me write it as I max into cos square of phi is pi by 2 divided by 2 will give you pi by 4. So this is I max into cos pi by 4 is 1 by root 2. The square of this is half, that is 1 by 2, or IQ is equal to I max by 2. So to find now is the ratio of IP to IQ. So IP by IQ is I max divided by I max by 2. So that should be equal to 2:1 because I max gets cancelled here. So the ratio is 2:1. So the correct answer is option A, 2:1. Now let's work out an interesting question, dear students. In Young's double slit experiment, one of the slits is wider than the other, so that the amplitude of the light from one slit is double that from the other slit. If IM is the maximum intensity, the resultant intensity I when they interfere at phase difference phi is given by options A. Im by 9 into 1 plus 8 cos square phi by 2. B. Im by 9 into 4 plus 5 cos phi. C. Im by 3 into 1 plus 2 cos square phi by 2. And D. Im by 5 into 1 plus 4 cos square phi by 2. What are we supposed to find out in this problem is to find the relation between I and Im, where Im is maximum intensity. So where I is the resultant intensity at a point where the phase difference is phi. But the condition here is that the two individual intensities are not the same. The two individual amplitudes are not the same. Let me say that the amplitude of the first wave is A and that from the other wave is twice A. That is A2 is equal to 2 times A. As a consequence of which the intensities can be written like this. The intensity of the light from the first source is I1 is equal to A square and let me call it as I. Similarly, intensity of light from the second source is given by A2 square which is 2A whole square, that is 4A square. So when A square is I, this becomes 4I. So these two are the intensities of light which interfere at the given point. And you have an expression for maximum intensity and resultant intensity at any point. The resultant intensity is given by IR is equal to, remember here you are not supposed to consider the expression IR is equal to I max into cos square phi by 2 or 4 I naught into cos square phi by 2 because the two individual intensities are not equal. When they are not equal, we'll just make use of this expression, that is IR is equal to I1 plus I2 plus 2 root I1 I2 into cos phi. If this is the expression for resultant intensity at any point where phase difference is phi, then you can write an expression for maximum intensity which is given to be M, which is given to be Im as I1 plus I2 plus 2 root I1 I2. That's all, because for maximum intensity your phase difference should be 0 or 2n pi in general and cos of phi should be equal to 1. So Im is simply I1 plus I2 plus 2 root I1 into I2, and since we already know the expressions for I1 and I2, let me substitute. In place of I1 it is I, plus in place of I2 it is 4I plus 2 into root of I into 4I. So this becomes 5I plus 2 into inside root I have 4I square, that becomes 2I. So 2 into 2I is 4I again. Let me write it as 2 into 2I. So 4I plus 5I is 9I is the maximum intensity Im. Let me keep this as this is. Now let me substitute for I1 and I2 in the expression for IR. I1 is I plus I2 is 4I plus 2 into root of I into 4I into cos phi as it is. So this is equal to 5i plus 2 into 2i is again 4i cos phi. Now I'll write this as, now you can have a look at the four options. Do we have any option which is close to 5i plus 4i cos phi? Actually, your option B seems to have a term which is similar to this, that is 4 plus 5 cos phi, but it is slightly different from what is obtained. So you'll have to go further. You'll have to look at the other three options which all contain cos square term. Now in order to get that cos square term, you'll have to make some little adjustments here. So what I'll do is I'll write this 5i as I plus 4i, so that you'll get 4i common here. So I'll get one more 4i cos phi as it is. Now I plus 4i plus 4i cos phi can be written as 4i into 1 plus cos phi. Now in this term of 1 plus cos phi, you have 2 cos square phi by 2. You can find that cos square term. So this becomes equal to I plus 4i into 1 plus cos phi is 2 cos square phi by 2. So this is IR. So IR is equal to I plus 8I cos square phi by 2. Now I'll take I common. So IR is equal to, when I take I common, I am left with 1 plus 8 cos square phi by 2. But resultant intensity, instead of writing it as IR, I think you can make use of I. So this I is the intensity which can be expressed in terms of I max, because we already obtained Im is equal to 9i, therefore I is equal to Im by 9. So in place of I can write Im by 9 into 1 plus 8 cos square phi by 2. So that's equal to the resultant intensity. So this is the correct expression for intensity, and that is clearly given in option A. Therefore option A is the correct answer. That is IR is equal to Im by 9 into 1 plus 8 cos square phi by 2.